Yay!
Yay! All right, now that we know the moment of inertia for a single point particle about some distant origin, the simplest case, now we can start building up more complex cases based on it. So what's better than one object? How about two objects? So suppose we have something like this. So we have a 2 kilogram mass and a 6 kilogram mass, and they're sort of tied together by some stick. And the idea is I don't have to worry about the stick. It's some really light stick so that the mass is really kind of negligible. So I've got these two masses, and they're, let's say, 12 meters apart. And I want to calculate the moment of inertia of this thing. Well, let's hold on a second. Not so fast. Let's talk about a related concept, which is going to be called the center of mass. And maybe you already know how to do this. What we want to know is where the center of mass is for this thing. Another way of putting it, some people call it the center of gravity or the balance point. Or you can think of it as like a seesaw, right? Where do you put the little fulcrum? Where do you put the balance point so that this thing will balance? And just from your intuition, you know, playing as kids or whatever, you sort of know that the center of mass is going to be closer to the more massive thing. That just sort of is something that would make sort of everyday sense. We'll show that, in fact, that's true. So, you know, you might imagine that if you were going to balance this thing, you might put a balance right, you know, it'd be over there somewhere. Let's figure out exactly where it is. But it should be closer to the more massive thing. Okay, here's how you do it. The center of mass is a weighted... Oops. I gotta spell weighted. A weighted average of where the masses are in the system. So how I'm going to figure it out is, okay, the position of the center of mass is just going to be, what do? I'm going to add up the positions of all the masses multiplied by their masses. So I'm going to sum over all the masses, each I. I'm going to sum all the masses. I'm going to sum their mass and their positions. And then I'm going to divide by the sum of all the masses. Okay, so maybe that's a confusing looking way to write it down, but that's sort of compact notation. Here's what it would be in this case, is that I've got two masses, so I'm going to sum together two things. Okay, here's the first trouble, or here's the first problem. What's the distance from what? I'm going to sum the masses times the distance from what? As we're going to show, the nice thing is that it doesn't make any difference. You can choose whatever point you want as long as you're consistent. So let's do this. I'll show you that it doesn't matter. Let's compute the position of the center of mass relative to the left-hand side of this thing, where the 2 kilogram mass is. Okay, so what I do is I take the mass times its distance away from the point that I've chosen as the origin, in this case, the left-hand edge, which is 0. That's actually a smart thing to do because you know that anything times 0 is 0. I don't even have to include that term, but I'm just writing it down, you know, just for completeness. Okay, and then I add, I'm summing all these things together, 6. What is its distance away from the point I've chosen? 12. And then what's the sum of all the masses together? Now, sometimes people mess this up because you say, oh, I didn't have to include the 2 before. I don't have to include it now. No, you do. You always have to include the 2 in the bottom. So it is all the masses added together. So this is 8. 6 plus 2. So what is that? 12 times 6, 72 divided by 8, 9. So this is going to be at 9 meters. Okay, so right about here. So this is 9 meters and 3 meters. Cool. So the center of mass of this thing is kind of closer to the 6, right? That makes sense. But watch. What if we do the position of the center of mass relative to the right-hand side? Let's see what we get. X, CM. From the right-hand side, I could choose any point I want to be the origin. So if I choose the right-hand side, what do I get? Well, I'm going to get, and here's where you have to be a little careful, 2 times, now, what is the position of the 2 relative to our new origin on the right-hand side? It's minus 12, right? The direction is important. So minus 12 goes here, plus 6 times, now that's 0, because that's our origin, still divided by 8. So what is that? Minus 24 divided by 8, minus 3. But doesn't that make sense, right? Where is the center of mass relative to the right-hand side? It's 3 meters to the left. So I'm getting 2 different answers. I'm getting 2 different numbers, but they're both describing the same point. So everything is all right. So no matter where you go, you can, I'll leave it as an exercise to you. If you want to solve this, try to find the center of mass and place your origin right in the middle at the 6 meter mark. And what you're going to find is you're going to get a different answer, but you're going to be describing exactly the same point. Right? So finding the center of mass, it doesn't matter from what point you do things. So that's why it's always kind of a good idea, if you have a whole bunch of masses, take one of them to be the origin, because that way you just don't have so many things to add together. All right, so that's how you find the center of mass of the thing. By the way, let's do a quick example. What if I have a 3D thing? I think I wrote one down. What if I have a mass here, and let's keep our big mass here. Let's say this is like 4 and 2 and 6. Right, same kind of idea. And let's just keep the measurements. Let's say this is 12 meters and this is 12 meters. Where's the center of mass of this thing? Now it's in 2D. So what you do is, if you want to find the center of mass in 2D, the position of the center of mass in 2D is going to be, well, it's just going to be the sum. I won't put the I in there. That's sort of understood. It's the sum of each mass times its position away from whatever origin you choose, divided by the sum of the masses. Right? It's the same idea, except now these are vectors. Now they're going to be vectors in 2D. So, I don't know. Let's just do it. Let's just see what happens. So, where is the center of mass of this thing? Let's choose, I mean, it looks like 2 would be a convenient choice for an origin, right? At the 2 kilogram mass. So, let's start there. So, we're going to have 2 times the vector 0, 0. Then I'm going to have a 6. Where is 6? It's at the position 12x and 0y. And let's see, I'm going to have a 4. And this is going to be at the position 0 and 12 in the y. And then I'm going to divide by the sum of all the masses. What's all of them added together? 12. Okay. So this looks like I'm going to have, 72. This is going to be the vector. 72 in the x, 48 in the y, and then I divide by the sum of the masses. And so what's this going to be? This is going to be the point 6, 4. So I don't know, that's right in the middle here, right? 6, I don't know, it's right there. It's here at 6, it's over here at 4. So here, there's the CM. Okay, 3 dimensions, you're doing exactly the same thing, except you're going to have an x, y, and a z component. But that's how you find the center of mass in multiple dimensions. So it's the same procedure, just you're using vectors instead of distances. So no problem. Okay, so what we want to do is we want to figure out the moment of inertia of this first thing. Let's go back to this object up here. What is the moment of inertia of this thing? Now, here's what's important. Whenever you calculate the moments of inertia, you always have to say, with respect to what? About what point are we going to spin this thing? Remember, moment of inertia is a rotational mass. So how is this thing going to rotate? Let's say we're going to rotate it about the left end. We're going to pin the left end and then swing everything around the left end. Okay, so the moment of inertia around the left end, well, each of those is going to contribute, we said each point mass is mr squared, right? So this is just going to be a sum of m r squared. The cool thing is that now we're squaring r, so that really is just a distance. I don't even care if it's positive or negative. So let's see what we get. I'm going to have a 2 times, I didn't really have to write that down, right? 2 times 0 squared plus 6 times 12 squared. And if you calculate, what is that? 144 times 6, what is that? 864. What are the units of moment of inertia? Well, it's mr squared, right? So it'd be kilogram meter squared. Not really intuitive units. Okay, there you go. So here's the moment of inertia about the left. Now, here's why we say the axis that you choose is important. What if I do the moment of inertia about the right? It's the same object, but now we're going to choose to spin it about the right-hand side. So now it's the 2 kilogram mass that's going to whirl around. We're going to pin the 6 kilogram mass. So now we're going to compute the moment of inertia, and we're going to get a different number. This is why this is kind of confusing to people, because you're used to, I mean, if something's got a mass of 6, it's got a mass of 6. It doesn't make any difference, how it's arranged or whatever. But here in rotational motion, it does make a difference. Rotational mass depends on how the thing rotates, what the axis of rotation is. So if I compute I and spin it about the right-hand mass, I'm going to get a different number. So I'm going to get 2 times negative 12 squared. See how the negative is not really going to matter, right? Mr squared plus 6 times 0 squared. And that's going to give me 288. I'm going to suppress the units. So it's a different number. In fact, it's a lower number. Remember, moment of inertia is the resistance to being accelerated. So if you spin it about the heavy mass, it's easier to spin. The moment of inertia is lower, right? Well, that kind of makes sense. We're not moving the heavy thing, so it shouldn't take as much effort, right, in some sense, to spin this thing. So that kind of makes sense. So we get a lower moment of inertia, lower resistance to being spun. I mean, just for kicks, why don't we do the moment of inertia around the middle part? What if I pin the middle of this thing so that both masses are spinning about the middle? So middle, what is that going to be? That's going to be 2 times minus 6 squared plus 6 times 6 squared. Who's that going to be? That's going to be 72 plus 216. Oh, look. I get the same number. That's really interesting. Is that the lowest number I could get? So it just so happened, this is sort of a coincidence, it just so happened that I got the same number for the moment of inertia about the right side and about the middle. But that's not the lowest it could be. We already know where the center of mass is, right? We've already computed that. So let's compute the moment of inertia about the center of mass. How about that? So at the center of mass, where is the 2? The 2 is going to be 9 away, and the 6 is going to be 3 away. So what's that going to be? 80, 162 plus 54. It's lower. It's lower than anything we got before. So how long do we want to continue playing this game? Like, where can we find the lowest? Where is it easiest to spin is what I'm getting at. So the lowest moment of inertia is where it's going to be easiest to spin. Do we have to keep hunting around until we find maybe there's some point that would be even lower than that? But what I'm going to say right now is that no, we've done it. We found it. Around the center of mass is the lowest. It's a minimum. That's something we're going to try to prove here in a subsequent little video. But I'm just going to assert right now that the center of mass, and you can try it for yourself, you can pick all sorts of different points, you're not going to find a lower moment of inertia than right there at the center of mass. It's sort of a magic point where an object is easiest to spin about its center of mass. Maybe that sort of makes physical sense to you. So we found the I. Let's find out, just for kicks, if this rotates at, let's say 20 RPM. Let's find the kinetic energy. Let's find the rotational kinetic energy of this thing. How much energy would it take to spin it up to this? Or how much energy would it take to stop this thing from rotating? If it rotates at 20 RPM, what does this mean? First of all, 20 RPM, that's not something we can plug into our equation, right? I mean, what we want to plug into is K is 1/2 I omega squared. Well, we know the I, we got the I, but we want the omega. And omega is in radians per second. So we have to convert RPM to radians per second. So let me show you how to do that a quick way, very, very quick way, because it's boring. But let's just do it. 20 revolutions per minute. I want to convert to radians per second, right? So I got to get rid of the minutes. Oops. Minutes, 60 seconds. Okay, so minutes goes away. So now I have revolutions per second, but I want radians, not revolutions. So then I have to multiply by 2 pi radians per revolution. Now I got it. Now I got radians per second. Now I'm all set. But look, what is that conversion factor? It's just 2 pi divided by 60. Right? I mean, you can figure out what that, you can plug that into your calculator if you want to. You can figure out the exact relationship. But 2 pi, I mean, that's like, isn't that like 6? It's just a little bit bigger than 6. So 6 divided by 60, that's like 1/10. So a really quick way to do this, like this is how you would do it exactly, right? To change this thing. But my advice is, when you're solving a problem the first time, just do it the quick way. Let's see roughly what the answer is going to be. So 2 pi divided by 60, that's like 1/10. We'll just move the decimal point one place over to the left. So 20 RPM is about the same as 2 radians per second. It's really close to that. Close enough for government work, as they say. So the kinetic energy is just going to be 1/2 times 216 times 2 squared. Our omega is 2. So what do we get when we do this? 108 times 4, 432 joules. There we go. So that's the kinetic energy of this thing as it spins around its center of mass. Cool. So next we're going to prove the little theorem. We didn't prove this, but we'll save that for a different video. Let's prove that the moment of inertia about the center of mass is a minimum. That's kind of cool.